Okay, we'll continue now.
Yes, sir.
So, the next method, I think I can describe about another couple of methods, and the other things you can follow similarly, and then you can learn the solve the equations, transcendental equation or a polynomial equations. Okay, now we will start with the method of false position. This sort of another method which is available for solving the equation. It's again iterative method. This is the oldest method for finding the real root of a nonlinear equation of x equal to 0 and closely resembles bisection method. It's closely resembles. It's not exactly the same thing. In this method also known as regular falsi or a method of cards. We choose 2 points A and B such that f of A, f of B are opposite signs. So this is what same thing we have done it there, but we are going to handle it in terms of a cards. It's called a sort of a slope-like thing. We are drawing a line, okay, where this is f of A and f of B are lying on the curve. Hence, a root must lie in between these points. As it's lying on the curve, therefore it must be, because there is a choose points A and B such that the opposite signs are possible. So therefore it should have a root. Hence a root must lie in between these points. Now the equation of card joining the 2 points is A f of A, B f of A is given by. See, this is very simple to understand because 2 points are given and you wanted to construct an equation of a straight line. This is what your method of constructing a straight line. This is nothing but the slope and multiply with this x minus a and take f of a, so you get a y. That's what it means. So it's nothing great here, and I think this is there in our high school onwards. 2 points are given how to find out the equation of a line. Okay, this is those 2 points you find out f of a, f of b, b minus a. It is equivalent to having this is something like a tangent or a slope between this point B and B, and x minus a into that factor, we find out the y coordinate can be found, which is equal to f of a. It's something like in a numerical integration when you perform, you do similar kind of things. So, therefore, this equation is known to us, well known to us. We have put it in this form for a given point A and B. After finding f of A, f of B, this can be used now as a regular falsi or a method of cards. The method of cards, why do you call it? This is the line which is going to pass through the curve. That's why it's called method of card. Okay, so the method consists in replacing part of the curve between the points A, f of A, B, f of B by means of a card joining these points, and taking the point of intersection of the card with the x-axis as an approximation to the root. So you take that, taking the point of intersection of the card with the x-axis. So this is the point of intersection of the card along this x-axis. This is the first possible route, and you can take it closer and closer and closer and closer and reach the curve. This is the curve y of x, y equal to f of x. This is a point and a b point, which is equal to a of a comma f of a, and b point is b of f of b. And this is the card which you have identified first, and this is the second card, third card, fourth card, fifth card. Iterate it systematically, and you reach until this point. Okay, then once you touch at this point, then you have a road. So that's the idea here. And see here, that is the point B is represented by this. This is the x-axis, this y-axis, and this is x-axis and y-axis. So in between, there's a positive and negative side in here. For this curve, I have a positive, and which means opposite sign is positive. Now you can select the card somewhere. It need not be at this point. Any point within this curve, you can select it so that it has a positive and negative, and start move towards. The card can move toward the point where it goes to, where the y of x goes to 0. Till that, you make an iteration and decide your number of iterations you want and your accuracy, all these things, and then simplify that, you get a result. That's the idea here. So you just find out what is the card that you Why we call it as a regular function? We do not know whether this is right or wrong. Okay? But regular, systematically you try to make these lines with a condition that you need to have positive and negative opposite signs are required. That's a condition which is required for this method. Okay? With that, we can move towards this card can move toward the point where y of x goes to 0. Look at that. That's the point where you need to have a. So that's what the point which we require, that is the root of this equations. Okay, so now you rewrite this equation and represent as a x1. So the method consists of replacing the part of the curve between the points by means of a card joining these points and taking the point of intersection of the card with the x-axis as an approximation to the root. The point of intersection in this case is obtained by putting y is equal to 0. Okay, in equation 2 points, thus we obtained. So we wanted to make that y equal to 0. That's the idea, no? Is it not? Y should become 0. So therefore, by putting that, I'll get an x1, which is equal to this, and multiply and simplify, you get a f of b, b f of b. That's all. F of b minus f of b. That's what your next point, x1. That is the first point, and I can go to the next point, x2, following this. Okay, this is the first approximation. Root for f of x equal to 0. If now x1, f of x1 and f of x are opposite signs, then root lies between a and x1, and we replace b by x1 in equation 2.7. That's the idea, and obtain the next approximation. Right? We replace a by x1 and generate the next approximation. This procedure is repeated till the root is obtained to the desired. It is similar to what you have seen in the bisection, but only thing here is doing it in terms of the card. Okay, now you have the figure 2.2 gives you the graphical representation of the method. This is the graphical representation of the method. The error criterion equation 2.0 can be used in this case also. The 2.5, what we have been described earlier, that can be used for the error criterion. It is similar to that. Now use this equation, do it iteratively, confirm it. The iterative procedure is right, and generalize it and make a Mathematica code for this regular function method to check it. So we will do that first part. What we do, we'll reproduce the results what has been given the text. Find the real root of an equation x cubed minus x minus 5 equal to 0. This is what your f of x, and make a plot and using the filling bottom. Filling bottom, this is filled. So if I don't have this, so if I don't add this is what we call. No? Curve, and this is the curve that we have. For a clarity, for a better representation, that's what this is. So we done a bit. Means below this curve, whatever which you have, that will be some color. The color also option will be on. This is by default, it gives this color. You can select the color the way you like it. Okay, so now it's clear that there is a root at somewhere between 2 to 2.2 goes to 0. So now you can start select the points between 2 to 3. Okay, I'm selecting the point between 2 to 3. F of x is already defined here. I'm going to find out what is f of a and f of b, taking a equal to 2, b equal to 3. That is what your equation here. Right? F of a, f of b, substitute a and b. I'm able to get this value of f of a and f of b. You can check it, but check it now. But a equal to 2, what happens? What is the value? Minus 1. Is it really happening? At a equal to 2. A equal to 2. What is going on? F of a is how much? 2 f of a is how much is that? F of b equal to 3 is 16. Because 316 will be there. Then will be equal to 2. This is the number which is minus 1. Because I think so, because this is a minus 5, there is only one unit here. Okay? You agree with me? This is one unit is passing through this at a, which is nothing but x equal to 2, and b, which is 3, which is 16, which is the curve which we are not shown. We extend this beyond not range. Confirm that whether this curve is right or not. 11, 12, 13, 14, 15, 16 should be here somewhere. So I'll just put it now. It's minus 5. I write only one list. Okay. I write like this only one list. It is equivalent to saying that take y alone. That's what it means. And if I give a list containing, this is I wanted to tell you people because you will get confused now. You can see here, I'm giving the plot range. If I give a list containing only 2 numbers, which will be taken only for the y. If I give both x and y if I want, then I have to add another list, and that should be put into the each containing each list contain 2 numbers. This is x initial point, okay? X end point. This is y initial and y end. Now you can see this is going to be minus 3 to plus 3, and it goes on, and then you can see 16, and one more point is here. This is 15 plus 1. This is 16. Then b equal to 3, it is y is equal to 16, and b equal to 2, it is equal to minus 1. This is the minus 1. Right?
Yes, sir.
Is that right? No? 2 and 3, correct? No? Agree? This is the minus 1 and this is the 16. Still you have any doubt? This is 2 now. Therefore, I am near the 2, looking for the y value. That's equal to minus 1. I'm substituting here. This is the equation which I'm having it now. Okay? Still you are not in a position to accept. Let me make a table of f of x, the range you want to have. Let me take x ranging from minus 3 to plus 3. X, I'm making a table so that you know what is x-axis. Steps of 1. Avoiding the other fractions. This is what I have. So if you wanted to make a x, f of x, both you can make a table now. Pair of quantity is table, and you can confirm it now. 2 minus 1, 3, 16. Other places also I have found this. And you can confirm all these values, they will be consistent. Okay, I have not shown the range. No, minus 3, 26, I have not shown. If you wanted to show that, then what you have to do? I have to add minus up to 30. Then I can see the curve. Okay, 30. So 26 will be somewhere here. 22, 24, 26. The point here. Okay, well, minus 3, this is it. So this is what the curve which we have, which has a change of sign at this point that we wanted to locate by using this method. That's the idea. It's clear for all of you. That is the point which I have taken. So you can see 2 What is it? 2 is 2 minus 1. That's here. That's the minus 1 which has been located. When b equal to 3, I have a 16. Okay, I hope it's clear. So don't get confused with these variables x. We are making it as a and b because that's the card which we are going to fix this point and this point we have fixed it. Okay, so first point you take, that's 2, corresponding value is the minus 1, and here another point which is equal to 3, corresponding value is 16. That is the point which we have fixed. So this point and these points have been taken to draw a card. That will be the first card which you will get it. So we are going to use that values with x to find out what is the x1 that is possible. Okay, somewhere it's going to be x1, somewhere it's sitting here. That has been fixed. 2.05. So we are close to that. Next, what you do? Find out f of x2. Again, it's negative. It's already negative. Here also negative. Then what is the root? Where does the root going to lie? Between 2 to 3 only again. Okay, so therefore I know this parameter now. I will see what I'm going to do. X2 f of b minus b into f of x2 divided by f of b f of x2. See this replacements. Okay. I think it's clear for you as negative sign.
Yes, sir.
Okay. Similarly, go to x3. Again, it's going to be negative sign. You are moving towards the region where 2 to 3 the root is lying. Go to f4. I'm just substituting it. If any change of sign, correspondingly just use the condition, change it, and then find out what is the value of the x4 and f of x4. Similarly, x5. Okay, if I use that, this is also again minus sign, so it started moving towards 2 to 3 only. Again, this is 2.094 next value. Find out that again minus sign. This happens to be conveniently this moving, therefore we don't have any problem. X7 also has been found. So we will try to check one more time every one of them. This is the f of A, f of B. X1 has been found. F of X1 is this. X2 has been found now. What does it mean? We are moving towards the crossing line that where y goes to 0. You can see this is the value of y f of x2 that's getting reduced as now. And this is next value f of 4 over, and f of 4 again is going towards 0. 5 again, further it goes to smaller value. 6 again goes to smaller value than what has been here. And 7. I'll find out what is f of x7. Right? It's smaller than this one. Okay, we are moving towards 0. So we have the number form x1, x2, x3, x4, x5 up to the number form of 10 decimal points which we have taken, and we are giving these numbers. These are the numbers that have been found, and you can cross check it. Well, this book must have given these numbers. Okay, you can cross check it and confirm yes, what is the logic that has been explained here is working well for the regular false or a false method for determining the roots. Okay, is it clear for all of you now so far? See, unless you do this, you cannot understand what is the logic that goes into the computation. Cannot understand. So once you have clear picture about each one of the substitution and number getting, and if you confirm it, yes, seems to be right. Now what you need, I need to write a program for this for an iterative form. That has been done here. Okay, regular policy 1, where I wanted to have the details about the table, the K, AK, CK, VK. Doesn't matter what are the name that you use, but you please note that this is what ultimately important for you. And start from K equal to 0, repeat the process, and the change of sign is there. That's also can accommodate properly. Then ask to print if necessary. Otherwise, at the end, if you want to have the root alone, you can write it in a simple form. Take the equation and the result outside. That also possible. Now we are giving the complete module has been written very compact form. Still, you can write it in a compact form, but we need to have some details to start with. But what is important is this equation is something which should be defined carefully, and that should be handled with if statement and while statement and whatever which you wanted to see them as an output that can be here. Okay, and print the C of C's, whatever you want. Instead of X, we are using possessive, that doesn't matter for us. Okay, so let's try to check whether this is going to work now. Yes, enter same equation which I'm going to give it now, and the regular false, what the input is expected, A0 and B0 and M. M is the number of iteration. So 12 iteration I have given it, 2 to 3, and I have a result up to 6. 10 power minus 6, the f of ck, f of x. This is nothing but y, this is becoming 0 to a greater extent. We have stopped here only 7 iteration, but we have gone up to 12 where the accuracy is better. Stop with 7, you have only 3-4 digits. Become a 6 digits accuracy. That's what is happening now. Okay, we'll get the numbers now. These are the numbers. Okay. So this programming part, basically the idea that whatever is explained has been implemented. And most of the commands what you have seen is already you are exposed. Okay, table form, printing, then append is just defining it initially here and append it. Okay, the output will be appended here. Whatever the output which you are getting, see the output will be appended here each stage, and that is being used here to tabulate it here. Okay, now you can check up to 7. Whatever we have done here, those numbers are available by the program. Whatever if it don't get it, then you have to cross check your program. Then make sure that you are getting it properly. See here 2.08823. This number, second number, third number, up to 7 numbers that you are getting. Seventh one is 2.09451. 94518093. It's a little difference here because you are number of digits. Here it goes with the 16 digits. There I stop with the 10 digits. So 16 digits, yeah. Print f of 6. This is 16 digits. Because after there is a 00. That's not printed. So this works well now. No problem with this. And you can change the function and cross check it. So there is a concise way of writing it is that I don't want to see intermediate steps, all of this. I just give the equation and get the output. So that for that, whatever is asked to print unnecessary things that can be taken it out. Because the program is working, you are sure and you are sure about it, then simply just give an input here and the regular function 2, 3. So I have already results what asking. What is needed at the end 2.0945. This is what the number, and this is what your f of x or f of c. That is the number which you are able to get it. So you can change the region now. Need not be okay. Right. You can go to extent of say let me take start from 0 if I take what happens. This, since we know where the root is lying, you try to give closest possible. I'll make it 4.75. One. The root is right now 2.01. So now 5, 4, 8, 3 and 4. That's still trying to move toward that. So from 4, 3 to 4. So probably here in this case, number. Okay, it's not a problem. 2.0955538. So close to that here, remember? So it can move even if you are going outside. This card can be this side or this side. So that will be taken care by the plus minus changes program. That A is less than that. See, sign part can be taken care. Such things can be written so that even if you are going to the left or right, you can come to the root. So all has been taken care. Okay, signs. You follow what I'm saying? The root need not be within that, either to the left or right. That doesn't matter. It starts somewhere and then it started moving towards the point where we are interested to have that y of x that should go to 0 at this point, or y should go to 0 at this point. Okay.
So you mean that root must not be bracketed?
No, not that's the beauty here. No bracketing here. Only regular function requires that. See, because one line with this 3 and 4 it starts and started moving towards that. That's how it does. See.
Okay, sir.
Wait. Because this signs change, now. Let's see here. F of
Yeah.
C, sin F of C. That takes care of that. That takes care of it. That's why you are see B equal to C, A equal to C. And then you have this sin of F of B equal to sin of F of C. With this change of signs, it takes care of it. But to be on safe side, better you can have a bracketing like where you are trying to accommodate the x value such that it will be always trying to lie between this so that you are sure about it. Okay. So now if you give a wider range for even for a 12 iteration, accuracy is going down. So then I have to increase the number of iterations, then that might be improving. You see the point? Wider range.
Yes, sir.
Number of iterations required is more. If I make it 12 iterations for the same thing, accuracy is limited for the wider range. Suppose I am close to that, say 2.3 now or 2.2, then you see the difference, no?
Yeah.
Then the
Accuracy
iteration I'm getting it to 10 power 15. So therefore, this is something which is required for you, depending on your computation capability. See, now your systems are so fast, it's not an issue. But olden days, these are all very difficult problems. They're all time-consuming computations all on those days. Now it's just a fraction of seconds. Okay, so therefore it's not an issue at all. When you use like IBM 1130 machine, IBM 1130 machine, this computation will take half an hour, 1 hour, even for this. So we will do a lot of exercise before we give this and make sure that you try to make a closest possible road so that my computation will be more accurate. So if I make this is same with the same region, it is all goes on. It's 2, 5 again. And suppose if I increase the iteration, it will not improve much because already I have come to the closest. Okay. How it's going on. And we make an all possible analysis and see what's happening. Similar route I'm trying to. Okay, let's see. I'll just overview how to. So the only thing is accuracy has reduced because you have made a wider range. Okay, even I reversed it, that doesn't matter for me. So if I make closer possible, even with the lesser iterations, I can get the results what I need. 15 efficiency and even less for an accuracy close to or minus 15. Okay. Right. Next is policy. Oh, okay. This is same thing, but you are just reading the words. That's all. As you said, do that I have not given it anyway. 0 probably. 1. Okay, number of iterations. Okay, so enter and see what's happening. Something wrong. So I think null because this one output has not been given. So 2, okay, 3, okay. Tolerance is 0.001. Okay, the number of iterations, something like that. We can make it, but we want to identify 10 iterations. This is the results. It's already found. Root is 2.0944 for the tolerance what I have given. The 2 to 3. Now we can also change the range. Instead of 2 to 3, you can have other. Same thing if I make it 2 to 2.2. Then you would see that within this you can have a better accuracies. Here I think limited to 3 zeros, 4 zeros, I can have 10 zeros. Okay, now you can visualize it. The regular falsy method, what you have learned now can be visually seen. How does it get moves? Okay. Same thing, there's nothing great here. Only thing now we are going to use some graphic option. Good time to see that we are going to see them visually how the roots getting converges. The same equation. This is the card which starts with 3. Same thing. Okay, I think here I had given 1.2 and 2.5. You can see this will be start moving towards this when you increase the iteration. Starting is 1.25 to 2.5. This is what the row. See, started moving now. Let's come to the next point. Next. You can see the convergence.
Yes, sir. Yes, sir.
You can see this. It converged. Number of iterations. So this is what they just to show in picture form that how this card varying from 1.2 to 2.5 with a number of iteration and 10 iteration, you are reaching to this point. It just converges over this slowly, step by step. This is one way to look at it. And we have another equation, x power 4 minus x square. What are the roots that is possible for this? Can anybody tell what is the root for this? How many roots and what is the value of them? You can do it. Solve 10. Solve x power 4 minus x square equal to 0. Solve for x. Got it? I have a result here already. Minus 1, 0, 0, plus 1. And solve. That's the root. Now I'm going to see that one of them minus 1 I'm going to see. This is the place where it crosses. Okay? So I wanted to just check whether it's right or wrong. For every iteration, this is the card which I have fixed it by fixing certain values. Okay. This is the x value, the range, and number of iterations. See. Next, let's come to that point. Move for that. You see how it's moving towards the road. Going now? Let's come here. We started from here, start from here. Let's come here, from here. Going toward that. Yes. I have minus 1 is the road which is lying between, you can see 0.5. This side we have started moving. Right. First. We are almost close to that. The number. You able to see that?
Yes, sir.
Starting from visually, I'm able to see how the root is. I started with the 0.5 to minus 1.1. This is the card, which means I have a plus minus change which are available in this, and that is being calculated by iteratively by increasing the number of iterations. Second iteration, third, fourth, fifth, sixth. So nicely you can see that gets red root is big. Time. Another root, positive one. Here I change this region. See? Minus 1.2, 0.5. But here I'm coming other way. 0.8 to 1.25. To find out the other root, which is plus 1. It's here. It's crossing. So same thing, just copy over it here, change the range alone, and do the so-called the manipulation of this. Value of n 1 by 1. Then see we started coming closer. If you want, we can add some more points so that you will be near to that. Say, takes something like 13 or 14 number or so that I almost reached. Already reached. Too crowded at this place because we are very close to that. And you can take it back and say, and this is of course you have an animation option. Slow down. And back again from 14. It's also nice to see. Mouse. Starts from the root and comes back to this position. And it's 21 it's moving one by one. So this is how we perform this computation here to find out the root. And feel that yes, the method has certain logic, it works very well. You can cross check it. Okay, there are other ways to improve this, and this will be a little better than the previous one because number of iteration goes down. Half interval search is a bit different. This is sort of an approaching point here to this where this slope is, or the y becomes 0 at this point. By this card, you're taking this and slope and take it to this point, and where this y goes to 0. Then that is the root. That's how this. So there is a mathematics here. This mathematics has been working well when you put it with this mathematical code. Okay, I hope it's clear for all of you. Any clarification?
Yes,
So now we can change your function. First, whatever function you try to do, first make sure that you change the function here. For example, I have a transcendental equation like x e power minus x minus 1 equal to 0. So, you know what I'm trying to see? This is the polynomial. Now, what I'm referring now, the equation is the x I have e power minus x. And this equation, and we wanted to find out the root. Okay, replace that function and do these all possible things. Generate the numbers first for the regular version method, and finally find root. This is mathematical code. Mathematica built-in function. Mathematica find root. Okay, this is equal to 0. And if the x value, I do not know what is the value to be given, but anyway, I'll just put it as this is the range and it says something. So now find row search step size tolerance, say something it says. Now we have to have some idea about this. Okay. So what do I do? Start the function, get an idea about what is going to happen. The x. That's the most thing. What I'm thinking about it, so that we have some idea about that. You know what's happening now? What is why this is statement is coming and what is really going on? What is the problem?
So that it's a -1 is making it below.
No, minus one is making it below 1. Okay, but it doesn't cross your line, no? Positive, negative. See, you have only the negative value all along. I don't think any region where you find it has a magnitude where it is going to cross 1. So suppose if I make this is equal to this is a problem. So let me try here whether it has a root or minus. Yeah, it has a root. This has a root. Hello? This is crossing this axis.
Yes, sir.
This is 0, 2, 4. Okay? This is minus. Hello? So instead of plus, I need to have a instead of minus, I need to have a plus sign. Then you will get a root. That is what the root is here. Hello? So this is what first thing you should do. Make sure that there is a root that is available. Suppose if it is completely at the bottom line, we don't have the root. Okay? So it is a sort of no root is available for that function. This is what it means. You can analyze this function, why it doesn't cross your positive, that is not allowed for this. This function doesn't permit any positive value. Right? 0, all the time it has a negative value because of the nature of the function between -2 to +2. It has all throughout having a negative value. Even if it is positive, there is a negative value. Okay, if I take say yes, it can go to the line, which is that's the so therefore change in the transcendental equation form where it crosses. Okay, where crossing is possible by crossing. Somewhere about 0.6. That can be 0.56. Now replace this starting from here onwards. What I'm suggesting, it should be start from here. I'm going to work out on a complete problem newly and substitute them, get an idea about how things are happening. Okay, then replace it here. Get the table and confirm it with the computation what you have right here. That should be consistent with your computation of this. Then other things can be repeated. And make if you want to add here the graphically you want to look at it, you can look at it that also. Just change the function. For example, I wanted to change the function now. What I explained is the function is what is the type? X over plus x, is it not? Right?
Yes, sir.
Yeah, it should be plus. And it should be -1. This is what your function is. And its root is lying between 0.56 somewhere, is it not? So let me take 1 to point minus 1. Here with the minus 1 plus 1 and look for the solution now. Whether I'm able to see that or not. Yes, it's here. Tangent between these curves and then I change it. Okay. So you find there is something strange that happens. So you have to optimize this. Okay, when you are changing these things. Number of so let me go to see 1 by 0 is encountered all possible things because minus 1 to plus 1 is taken. So therefore what you have to do is start from 0.1 to 1 in the range and then look for it that will be better than what you are trying to search for it now. Okay. You're able to see? Earlier it was when I put minus 1 to plus 1, this infinity, all other things have entered. Okay, when x reaches that, there are 0 is coming, therefore it complicates your plot. And now you can see this is improving. It's approaching the what you need. You don't have to even tensed. The nitrate is also required, not required. It is here. Okay, do this. Now it's going to reaching plus and the reach close to that. Close to the reach. Okay, so now I didn't do anything except this changing this function. But how it is being implemented that we wanted to understand means you have to select some such function, make sure that you are calculating all of them consistently. That should be reproduced through the programs and visually you just check it. Yes, what I did is right. When you do that, you have to take care of all systems, see the limitations of the functions. If you put minus 1 to plus 1, it gives all nonsense plots that it gives. See? Keyboard, but when I change, see, it goes to 63, all sorts of things that are happening. Which are all not required. In fact, it's blinking, doesn't know what to do. See, 1 by 0 is encountered. Our infinity, e power complex infinity, all sorts of things are happening because you have an e power x into e power x minus 1. So therefore, you should be careful about those things. And then alter it to say 0.4 if I take, this will be fine now. Then we'll try to use that. Okay. I make this is 0.8 again. And sitting here. Then I'll look for it.
Sir, in bisection method, we know how much accuracy we want. But here, is there any
No,
way?
no. Please read this here. Already that has been explained. The error criterion equation 2.5 can be used in this case also. This is actually for the bisection. Same criteria is
Same
followed.
can be used here.
Yes. That's right. So similar thing can be followed. Describe that. Okay, error criterion is similar to that. Follow that and then calculate them for a given range and what could be the error that is possible for the given iteration, for given number of iteration. So this is what the results that we have. Okay, so I'm fine now. And see, this kind of analysis is required to start with. You have to go through the function by plotting it. Then find root is already available for you with the Mathematica built-in function. With that range, you have some idea. Then you can pick out the range what you want to do. Then you can see, as I said, this logic is very important. What is happening over the method? What will be the algorithm that you should follow? That should be understandable first, and then you can play with that. Okay, so we'll go to the next part of it. We'll move these things along. It's only back to save. So anything you wanted to clarify? Clarification you can hear? I just followed the book of Sastri. Sastri has given same problem. And followed by that he has given some more problems. Maybe that you should follow that. Follow them, it would be nice because he has given some more examples. He has given the numbers and some method he has given it. Those numbers you produce when you have a sine and cosine, okay, sine form, sine combinations, exponential, and then polynomial equations. But those things in this form, numbers have been given, and our job is do this and then confirm it. Okay. Is it fine now? We'll go to the next part of it where we are going to learn addition.
Yes, sir.
Next
Yes,
part
sir.
is regular policy is over. We'll explain one more method, namely this Newton-Raphson method. That is still is much simpler compared to this. Okay. See, getting this equation of Newton-Raphson formula is very simple. This method is generally used to improve the result obtained by one of the previous methods. Let x0 be an approximate root of f of x equal to 0 and let x1 equal to x0 plus h. This is the root and a very small value of x is added that we assume it is equal to x1. Be the correct root so that f of x1 equal to 0. Expanding this using Taylor series. This is the Taylor series which you are already learned about it. Neglecting the second order, you will neglect this higher order derivatives. We have this. This equal to 0. Okay. This point should be clear for f of x1. Expanding this and equal to 0. This is what the result that you have. H can be found as connecting between the derivative of the function at x0 and the function at x0. This is the connection between these two by this expansion, neglecting the second order and the higher orders. A better approximation than x0 is therefore given by x1 equal to x0 minus this initial value of x0, f of x0, f prime of x0. Successive approximations are given. Go ahead. X of n plus 1 equal to xn minus f of xn, f prime of xn. So this is nothing but you are finding an equation of a tangent to the curve. Okay, that has been obtained like this. That tangent is being fixed to these coordinate positions. This is f prime. This f prime of x0 is tangent at a point x0, and the other things are known to us. Then that has been approximated by using this Taylor series in this form. There are many ways to derive. This is one of the ways that results have been given. Okay, so this is the Newton-Raphson formula, which is very simple. X of n plus 1 iterative form. This is 0, this is 1. Therefore, n plus 1 equal to n connecting. That's how it has been given. 0 and 1. If it is 2, then it will be x1. Therefore, n means n plus 1 and xn. This is what it is. Geometrically, the method consists in replacing a part of the curve between the points x0 and f of 0. Geometrically, the method consists in replacing the part of the curve between the points x0 and f of x0 and the x-axis. And the x-axis by means of a tangent to the curve at the point. And it is described graphically in figure 2.3. Okay, it can be used for solving both algebraic and transcendental equations, and it can be used with the roots or complex also. So complex roots also can be obtained. So maybe geometrical picture to refer it better. Yes, here. What the geometry picture. This is the curve with a tangent. This tangent you try to take it to the at this point. That's the idea. Okay. But starting from x0, x1, push, then take the tangent and into this. See, look at the methods, almost similar one by one. If you can look at carefully, this seems to be similar ideas are there, but only thing they are the way in which we are going to implement it. That some of them will take longer time, some of them will take a lesser time. Therefore, it would be nice to see all of them carefully and then try to see which one has an advantage compared to the other. There will be some advantages, there will be some disadvantages. All sorts of things that are happening with these equations. So this is the picture or a graphical representation. Geometrically, you can see that there is a curve here, then you are fixing the tangent here, P of x0, y0, and then that tangent has an x1. Next, you improve this tangent position in such a way that finally you will end up with the tangent point at this point. Tangent itself you are trying to bring it here through this equations and through this expression what I have derived here. This is the equations. Okay, there are other ways to write it, and higher orders also can be handled. Now we are going to work out that. Just going to take this. How do I make it? You can look at this. How I am copying it. Snipping to take out this picture from here. And then snip it. Go there. And put the picture in this geometry form below this. But before that, you have to convert a textual form and then so you got it now. I have this picture here now, which I missed to figure 220. Sorry. Okay, so this can also be that easy. It's not a difficult thing at all. So let's look at this example now. Same example, in fact, whatever which we have done earlier, same example we are trying to use, but we are going to see the multiple examples, other cases, other typical functions that we have. The function is here now. Fine. Take this equation now. First step is f of x0. I will replace it. It's possible to substitute. I'm going to do this x1 now to start with. Xn minus f of xn, f prime of xn. Xn of xn, I'm going to substitute in x0. That's what I am doing here. Then, after substituting this xn is x0, x0 I'm substituting is a number 2. Okay? See how this is 1 slash is a variable change. But after changing the variable, I'm going to make a substitution to x0. First step is xn becomes x0. Then x0 I am giving a number. Therefore, double slash dot. That will take care of the substitution for this the number. Okay. This is not necessary, but this step is I am given. So that first step as an x0 I am going to write it, and then substitute the x0 as 2, which leads to 2.1. First step is this. Okay. Now x2 by substituting xn equal to x1. This is x1 substituted here. This is the number I'm getting. This is x2. Number form I'm writing it as this. This is what the number is you have. Next is x3. Substitute the x2 here. Replace xn by x2. This is the third step. You can go ahead. Number of steps. But 2 to 3 iterations is enough. Whereas when you try here, the previous problems, the number of iterations is 10, 12, 15, depending on the accuracy. But here, within 2 to 3 steps, you find that the root what you need is already here with a 3 to 4 decimal of accuracy. So now the number of iterations drastically get reduced by this Newton-Raphson method. So that's why I have taken the same problem and show 3 iterations. You look at the previous problems what we have tried, there must be at least, for this you need to have 7 to 8 iterations for an accuracy of say fourth decimal or so, or fifth decimal. Here it is just 3 steps enough to reach this accuracy. Okay, so there is an advantage over these other methods. That's why this is generally most powerful one compared. But still, there is other problems. You look at the early days computation point of view. So this example demonstrates that Newton-Raphson method converges more rapidly than the method described in the previous section, since this requires fewer iterations to obtain the specified accuracy. But since 2 functions evaluations are required for each iteration, Newton-Raphson method requires more computing time. Number of iterations less, computing time goes up because it has to find the function every time, and the derivative also it has to find every time. 2 of them should be evaluated. Whereas previous things you don't have this. Okay, this is directly substitute and then simplify, get the results in one step. Here it's the 2 functions you have to have. Functions also required, and its derivative is also required for every one of the steps. So therefore, in terms of computational time, this is required little more time. Okay, so this is the simplest method that you have, just by looking at the tangents of the function and the function tangents, and then repeat it iteratively and try to bring it to the point where the tangent is lying at exactly at the 0 point. That's what the idea here. It has been done. So Mathematica code, here is the Mathematica code. Surprised that this is only 1 line code. Okay, but this is a new Mathematica code that we have to learn. Function is available. I have the hash here and x0, and n is the number of iterations. This is the number of iterations. And the region x where it is lying. And this is the function. This is the statement which is enough for implementing it. But this is nothing but your function, and a derivative one time is the on this function. Change this hash with x0 as a starting value. You can go step by step, and depending on the number of iterations, you get the results. So this is what the step here. Xn is this, and then function in the numerator, derivative and the denominator, which is the first derivative. And this is and with a hash and x0 you can go to the number of iterations that you need that can be fixed when you give the input. But with here it is uses so-called the nest list. What is this nest list? There are 2 things available. One is the nesting, N-E-S-T, and nest list. This is the nest. What is the meaning of nest here? So you can see the nest here. Nest f, comma x, comma 3. What does it mean? F of x is a function for the f of x. This value find it, substitute again back to this f as an x. Again, you substitute this back again to the x. So first step is f of x. That will become input for the next f of x. So f of x. Then next it will become f of x. So this is the nesting. Repeat. Goes inside, computation is done. Repeat. Say for example, if you do it for about 6 times, this is what the meaning of that. 6 times. Okay, next, let's take this one. Hash, square of that, repeat it, and you are able to see that 3 times if repeated, you are getting the number here, square of it. So maybe you can see here some numbers here. We try to see where you can have an easy form to understand. Yes, you can see. This is kind of a simple one. Next, 1 by 1 plus hash and x comma 5. Okay. Take it to twice. Follow what is happening? Or let me write it only once nesting. First nesting. This become a substitution for x. Follow? 1 by 1 plus divided by 1 plus of 1 by 1 plus x. That is what the meaning of the first nesting. Getting it? Hope it's clear for all of you. I'll repeat again. This is nesting. First function is this. This function is going to be the substitution for the next x as it is. Go to
Whatever be the result, that would be substituted in the next.
first thing, whatever you have, the whole thing is substituted for x. So now it is going to be which here? One what
Yes,
I
sir.
have seen 1 by 1. That's substituted here. If I go ahead with third time, that x is substituted in the denominator again. See, this x will be substituted again in the denominator if I go to the fourth time. This is substituted again in the time. That is what the meaning of the nest. Okay. And nesting. Okay. So is there anything still easier for him? In fact, you can do the nesting with the strings and other things also. Nest list, this is also nesting. There are certain things you may have a difficulty in understanding. The nest listing is done here.
Coach
too.
curve
So
and
this is the bifurcation.
the coach
This is
curve.
Yeah, coach curve, yes. Coach curves and other places that will be very much useful. So this is the nest. Nest list means you have a list, that's all. Nesting is done, but it's on the list it is being done. So that's how it's going to be there. So list is function will be there to start with. You apply again and again over the function and repeat the process, which is similar to, you can see, what does it mean? I have an f is applied function on x. F of x is the first value. This f of x become input for the next f of x. Then f of x is the input for the next f of a function input. Like that, it goes up to 6 times. That has been shown here. That's what the meaning of that nesting. So use this nesting business here. Nest list again. I think that will be easy for you to still easier to understand. This is nest. Nest list means I have a list here up to 10. And start from 0 to 10. So you add 1 by 1. Write it. 0 as the first step. Second is 1. Third one is add with that 2. So that is being taken care by the statement. Next list up to 10. So the list has been prepared. We are getting it as a continuous number. This can be used for generating even the continuous number. Like a range you write now, I'm getting it. Okay. It's the next list. This is equivalent to range. I have add range 100. That range can also be done by using this. Next, what is happening here? What is happening? Then in this nest list, what is happening? Each time, the number what you get is being multiplied by 2 every time. That is the nesting, nah? That's what the nesting list up to 10. You can see here 1, 2, 4, 8, 16. It's being multiplied. See, 16 becomes 32 again multiplied. That nesting will be continuing up to 10. You can go ahead with this number the way you like. So let me take something special about this number 64. You know what is this special number?
64 bit.
Yeah, it's 64 bit. This is the number of, you can find out the bytes and other things. So this is 64 times when we multiply this is what the number that you will be getting it. Okay, follow? This is easy for you to understand. You know chessboard? Everybody is familiar with chessboard. How many boxes you have? Black and white?
64.
64 of them are there. Okay, now each one of them you place it. First you place it, number one coin. Okay, 1 paise, one of them. Second, you multiply by that to put it that many number of coins. Third one, you multiply by the previous one, put it in the third one. Fourth one, you multiply that to again and put that many number of coins. You go up to 64. This many number of paise, you will get it at the end. And you know how much is this money? Okay? You follow what I'm saying? This is the number you'll get at the 64th box. This much of paise you have. This you converted into what? What happened now? Between these. What would happen? This is the paise which we have. Each one box, I'm starting with 1 paise, first box. Second box, I'm putting a 2 paise. Multiply that, put it in the third box, 4 paise. Then 8 paise in the 1, 2, 3, 4th box. 16 paise in the 5th box. Go on. Continue that. This is what the number of paise that you will get it for a 64 box if you do that. Multiply, you divide by 100. This is going to be your what? What do you get?
Rupees.
This is what you will get it. This is the money you will get it. Okay, and this you multiply again by 100. What would you get? This many hundreds you will get. Multiply this by 1000. This many number of 1000 that you have. What you have right now, 2000 rupees available now. This many number of 2000 rupees that you have. You see what's happening now. How big is this number? How you see the intensity of the numbers when you go ahead with this just by doubling it each time. Okay? Follow what I'm saying? And this is the number that is what having this many number of 2000 rupee notes that you will have. Okay? This is converting into rupees and divide by 2000. This leads to this much number of pi that you have. And this simple logic is that adding, doubling at each box. Somebody asked to put, okay, start from 1 paise from each box, please provide me up to 64. Okay, doubling each time. And you will become a billionaire. Okay. So this is what happens with numbers. So that numbering is handled like this, and this is how the nesting is done. I think you understand how the number intensity goes up when you do such things. Okay, intensity becomes too much. You can really feel this number is too high, big number. With a simple chessboard box which you would like to handle, by just doubling each one of the box, then making is there are good stories are available on this. Okay, so if you get a chance, you can go through the history of this chessboard, who has discovered and what are the stories about this chessboard. So please go through that and you find time. So it will be interesting to see that such numbers are possible. Okay, so next list can do this such kind of simple things, and here it's completely different. This is doubling it. And what is happening here?
The mobile എന്തെന്നാ ആള് കുറഞ്ഞു.
What happened here? This audio was okay. So now you can see next list again. Again 2 only, but something else is happening here. Something else is happening. This number already I found here. It's at 1, 2, 3, 4, 5, 6, 7th digit. What I have at the 64th digit, which is available here. Correct? You follow? The number what you have here. Are you able to see that? 1, 2, 3, 4, 5, 6, 7th digit, what you have here, it is available here as a 64th digits. What is that really happening here? Each time,
Powering by 2.
whatever which you have, that's being powered. Okay, you can see 2 square, then this become 4 square. This is 250, this is 16 square. This is the square of this number is the square of 256. This number is square of this number. And by the time we have already reached here. So next list does this with a simple AND statement with a square, hash square, 2,6. Okay? That's the greatness. And you look at here, it's again next list. You can understand clearly. X, 1 plus x square, 1 plus whole square. Here. Again, square. This is what happens. So this is another way to create a such thing. So which means iteratively there is a possibility, because you can see this is what actually happening here. It goes to the second stage, third stage, fourth stage iteratively. It's like a nesting. So therefore nest list idea has been used here. It is nested here. You can see here. The step whatever which you have written here, it is nested. See? X0, X1, X2, X3, like that it goes, it is nested. So that nesting can be used here and apply this on this function and repeat it number of times to starting with this range of values x, x0 and fix the number of iterations that we want. That is being defined here with this nest list. The nest list which can imply that how many number of times you are going to nest the list. That is what is happening. It's like this is done.
So that color is X is red in color.
It's just showing as a variable. That doesn't matter. You can change it to
okay.
the. That's not a problem. Okay, just show that x is the variable here. Okay, so just an indication of that. It can be removed also for the purpose of indication has been given. So now this can be run out here so that if it is small numbers, smaller number. This is again start with 6 so that you don't have problem occupying the space, and this is the 7th digit that we have. So nest list idea, that list list idea can be implemented here. Now you can see, I'm going to show you the numbers here. Newton's method list. That is what the line of this one line statement. I have to implement it now by shift and tab. Done. I'm going to see that numbers here. 4 numbers what has been found earlier. This is the function. This is the function that is supposed to be given here. Okay. And then the range of x starting from range here is the x, comma 2.0. I'm starting from 2.0 to x is the variable starts from 2.0 and go to the x values, and then 4 number of iterations. Instead of 4, I can have a 10 iteration. So that doesn't matter to me. Almost reach the constant value by say about 5-6 decimals accuracy. But here it is automatically takes check number form. And this is given at 820. It's already terminated, so there are other numbers that are 10 digits. If you want to have 16 digits, you can have 16 digit number form. Okay. The number form you put automatically 16 digits of things are required, and if you wanted to see any improvement, is it improving now further? 4, 542327. It's almost 16 digit accuracy. By that time it has come here itself. Okay. See, there is a change here. From here to this change. And hereafter, I don't think any change. So it's already have a 16 digit of accuracy by 1, 2, 3, 4, 5, 6 iteration. You have it. That's all. It's correct now. So it's enough to have a 6 iteration. Let me put 7 so that same result will be repeated. Right? What happened now? 1, 2, 3, 4, fifth iteration. We have this one 2, 3, 2, 3. That fifth iteration we are already. Both these are already available. 16. Okay, these are the results. Find root now. Probably number form. Have. Number form, number of digits. Okay. So this automatically find root selects the best method that is available for solving such equation that is found. This is specifically for a Newton's method, Newton-Raphson method. This is the question that we have. So and the same. Okay, now I have 1, 2, 3, 4 function at a time. What to see by grouping them in practice form. See the results on the screen as a pictorial representation. Stay interesting. That's all. Okay, other things are connected to the display of the results. Newton method, and then this is the manipulation for it. Now, well, so this is the negative and positive numbers, the number of iterations. Okay, this is only one iteration. This is the iteration. You can have something like 5 iterations. This zero equation, zero root, I'm not interested. Maybe I can search for this root. So I can change the x0 initial value. Okay, so that I can go near to this. Make sure that Newton function is working very nicely on that. Okay. It's good. Jumping. See how this starts from here, it goes here, then comes back, again goes down. So it makes connect the data now where what are the points that are available. And finally, the arrow will touches this root point. 3.1459 is the root for this sin x. This is sin x, correct? You can see here.
Yes, sir.
This is precisely that pictorial form. I'm started from here, then goes here, then come back to this, and then started touching this point. So 6 iteration, I have this result. That's what the meaning of this. Do same thing with the cos. Then you have 2 roots that are available. Okay, one of them will be fixed by. See the red is there already. Maybe you can select it far away and then make some more. Right, it's going now. Go around, and then touches. So this is the root 1.5708 radians. And if you want to find the other one, what you have to do, you have to select the x0 properly. Go to the away from that, and I will start picking up. Yes, the other root we are getting 4.71. Okay, 439 is the root. Okay, 3.5. No, 4.7. What happened to this? Yeah, we are just making a plot of cos 0 to 2 pi. Okay, that's fine. 2 pi is less than 2 pi. You have this. So this is one root, this is another root. By selecting appropriately the x0, I'm able to pick it up. So this is the. When I select this, you are coming to this. And if you know go it other way around somewhere, and it goes to this root. So this is the multiple roots can be found easily by varying this. This is for this cos. This equation is what we have already seen. Okay. Which you can select the. You can see it starts from somewhere. 1 by 1, 1 by 9. It starts from. We start from 5. First step, second step, third step, fourth step. Let's come. You can take closer and closer, number of steps goes down. You can see here. Okay, it's not tangent. And finally, the tangent becomes which y equals to 0. It's touching this axis. Okay, this is the idea here, and you can have 4 iterations, 3 iterations, 2 iterations. You have only 2. This is, see, it's not touching this point now with the 2 iteration. Okay, you don't have the complete root is not available. No, you cannot come to the actual value of the root. Okay, add one more. We're coming closer to it. Maybe add another. Still improving. Fifth one. Like that, you can go on and make sure that we have a precisely the root of the gain. This is what the starting and the goes to this form. So this is what visually one can see the Newton function also. Okay. About 3 methods we have seen so far. We have clear-cut picture about the theory behind each one of the method. Produce the results, whatever is given in the texts, and then taken various functions or different functions. In Mathematica, code has been developed, and then we have using the Mathematica statements also already available for substitute and comparing. We are able to get the exactly same numbers. So this is what should do whenever you learn any of the numerical techniques. Okay, so we'll stop here, and if you have any questions, we can have some discussions. Okay.
This Newton-Raphson figure is much better than the previous one. Convergence of the root.
Yeah, this is tangent now.
Yeah.
Tangent coming converging towards the root. The previous one you have a plus minus
sinusoidal one. All on a sudden it is switching over to the next root.
Of course, the x0 shifts.
Yeah.
You are shifting x0, so you can visually feel it. Whereas the previous 2 methods need to have a plus minus change in the y-axis. Is it not? Y coordinates.
Yes, sir.
Here you don't have that.
And here the degree of convergence, is there any
much faster?
Yeah, but any way we can quantify it?
Of course, number of iteration you can take this. See, this already I solved now. This equation, x cube minus 2x minus 5.
Yeah.
With the various methods I have already done. Look at the same accuracy what you have with the number of iteration. If you wanted to have the same accuracy for the same number what you have with this 9 iteration, there you may have to have 20, 25, 30, 35 like that. Or instead of that, what you have to do, you put it in a number form, vary the number of iteration and compare it each time. You have a Newton-Raphson method, you have a regular falsy, you have a bisection. Okay? All the 3, you will make a comparison with the number of iteration for a given function and check how much is going to be the differences. I am sure that Newton-Raphson will be in terms
much
of
faster.
Much faster. But at the same time, it requires the evaluation of the 2 functions. Function should be evaluated, derivative also should be evaluated. Sometimes this will be an issue when you go for a bigger functions, iterative functions.
Okay.
You nest list, for example, you mentioned about the coach curve.
Yeah. No?
There you have to be careful. It will be much more time consuming because of the derivative and the function. Because it goes in a nest list in a bigger function become too big. It will take longer time. See, suppose n is nest list is 100 times. F of x, initial first one will be going inside 100 times to evaluate it.
Yeah. It is multiplied and multiplied.
Yeah, it will take a hell of a lot of time. So you should be very careful about selecting the methods also. See, for a simple calculation, it looks very simple. Whereas f of x, for example, nest list, now what we have seen. If you make it for 100 times, now, you see how much time is going to be there, and imagine what would happen to the derivative.
Yes, sir.
Function is there, nested by 100 times. Derivative should also be nested by 100 times now. So it will take hell of a lot of time. So therefore, it should be careful. For this function, it appears to be great. But when it comes to really the complicated things like what you would like to see, like post curves for around 10 power 3, 10 power 4, 10 power 5 times is going to be a big problem for computational time. So therefore, at that time you see that what is to be done so that you will take care of your computation time also. That's what here is here given again. It requires more computing time when you go for this one, particularly with the nest list. Okay. Here nest list 4 times or 5 times, 6 times itself is going to be a very big function. The derivative also. So we are not showing that explicitly, but if you try to look at the form of a function, this is going to be a big function now. So, because it's a simple computation, it gives the result immediately. But when it comes to the real problems, it's going to be heavy computation for the machines. The computation. Okay. The ideas are very clear now, so we can think about applying to the problems. In fact, it has been used in fractals number of places, international method. Fractals have been done a lot based on this method. Okay, any other questions from students? So, I'll send you these materials, both